Now, when I do the picture for this one, it's going to look like that picture that I did with the figure skater. It's going to have a level surface. So we're going to have a level surface. Oops. And I'm going to have a person who is running on that surface. And since they're running on ice, ice is pretty slippery, and so if they push off too hard, their foot's going to slip. What I want to know is how much friction is available. You know, how much can I, as long as I'm within the friction value, my foot won't slip. So the direction of friction, if the foot slips at all, the foot is going to slip back. So that means friction is in the forward direction. It's preventing my foot from slipping back when I push too hard. So my picture is going to have friction in that direction. And you know, some problems I put, you know, everything right in the middle of the object here, but I'm putting it down here because it's specifically happening right there. That's where the forces are happening, so I'm putting it right down there. So that's friction. Now, if I want the maximum possible acceleration, then I want all of the friction available. I'm going to apply a force that's equal to the friction available, because the bigger the applied force is, the more I can accelerate. The harder I push off the ground, the harder the ground pushes me forward. And the more that the ground pushes me forward, the faster I accelerate. So if this value right here was 100 newtons, then yeah, I can push with 70 newtons, 80 newtons, 90 newtons, and I'm not going to slip, and I will be able to run. But I want the maximum acceleration. So I want to use all of it. I want to push it right to the envelope, that if I go any harder than that, I will slip. So I want to be right on the verge of slipping, and right on the verge of slipping would be when these two things are equal. Well, you still have the forces in the vertical direction, so you still have the weight in that direction, and you still have the normal force in that direction. So labeling them, that's your weight, and that's your normal force. So there's your picture as far as the vectors are on the picture. And now I'm going to just label what I know. So the mass of this person, so this person has a mass of 65 kilograms. All right, so that's the mass of the person. The coefficient of static friction between his shoes and the ice is 0.160. So that 0.160, that is the coefficient of friction. And we're looking for the acceleration. Now, it's a little bit tricky for this problem because I've had people in the other class saying, well, don't I get 0? If these two things balance out, then they equal 0. And if they equal 0, then I'm not accelerating at all. But for every action force, there's an equal and opposite reaction force. So what I'm drawing on the board right now, this is the force, this is the reactive force caused by pushing off the ground. And this I'm just going to call generic F, even though it's going to be equal in magnitude to the applied force. Because when I push off the ground pushes me forward. And the ground pushing me forward is the only force that's acting on me in the direction of me. You know, I want to run to the right. Or this man wants to run to the right. I'm calling the man me. All right, so I want to go, so whatever that is, that's going to be the unbalanced force that's going to cause this person to accelerate. So once I have the picture, I'm going to write my descriptive equation. So when I sum up my forces in the x direction, I have friction actually in the positive direction here. So I'm going to have friction minus Fa equals Ma, but we want no slipping and we want maximum acceleration. So we want the applied force to use up all the friction. To use up all the friction available so that I'm pushing as hard as I possibly can. Because the harder I push, the greater the force, the greater the force, the greater the acceleration. So that's my equation in the x direction. If I sum up the forces in the y direction, same as always. Fn minus W, well, as always in a level surface with a horizontal applied force. So there's my equation in the y direction. Any questions with that? So now I just solve what I can solve, and let's see. I'll just, rather than ask, because a lot of you want, you're doing the other work. So the first thing I would do is I have the mass, I want the weight. So I'm going to get the weight from the mass. So I'm going to get W equals mg. And so the mass is 65 kilograms. G is 9.8 meters per second squared. And if I multiply 65 times 9.8, what do I get? I get 637. So 637, there is the weight. Now, if I know the weight, I know the normal force, because this equation says they're equal. Fn minus W, so they're equal. So if I know the weight, I know the normal force. So the normal force equals the weight, so that also equals 637 newtons. Now that I know the normal force, and I know the coefficient of friction. So now I can solve for friction. So friction equals mu Fn. So mu is 0.160, and the normal force is 637 newtons. And if I solve that, I get 101.92, so that equals 102. So 102 newtons. Well, look at this equation right here, the x equation. Friction minus Fa in this problem equals 0, so those two are equal. So friction equals 102. To get the maximum possible acceleration, that has to be 102. So I'm going to write that Fa equals friction, which equals 102 newtons. Now, that number that I just solved, if that's 102, then that's 102. That's the force that's causing me to accelerate. So to solve for the acceleration in this problem, it's going to be F divided by M. The F being the unbalanced force on the person, which is caused by the ground. Because I pushed off the ground pushes me forward and makes me accelerate. So it's going to be 102 newtons divided by the mass, which is 65 kilograms. So that's bigger than 1 and less than 2. So it's going to be 1 point something. And what did I give you for that? 1.57. So that is the solution to this problem. I thought this was the trickiest one because it didn't align exactly like the other ones, and like the sample problem I did, it was a little bit different. Probably you wouldn't see this particular one on the test. You'd see more of the basic, a block is being pulled by something.